All right, welcome back, everyone. I hope you're fueled with coffee. So yes, I'm a researcher and educator in the domain of neurotechnology and brain-computer interfacing. And I would like to make it my mission today to introduce this technology to you under 4 subtopics. I would like to talk about how it works. I know there is a lot of hype around it, with Neuralink also coming into picture. So I would like you to know basically what are the under-hood mechanisms of the systems. Where is it applied? Does it have any applications for us, the healthy people? And where are the challenges and the ethical considerations for the future? All right, starting with how it works. Imagine you have a paralyzed patient or a war veteran who have lost their ability to move, or they have lost one of their hands. And now they want to ride their wheelchair or move these neural prosthetics just by their brain, by their mind, by the ability to imagine movement. That's where brain-computer interfacing comes into the picture. The ambition of this system is to connect, to bridge the human brain and the external machine. The first thing we will need in this system is a neuroimaging tool, right? So there should be a way for us to actually collect data from the brain. And there are 2 categories of these tools that we can apply to collect brain signals. One of them are invasive chips, where you have to go through surgical procedures and get an implant in your brain. And then the other healthy way, non-invasive way of it is to wear wearable technology. One of them is electroencephalogram, in short EEG, where we collect spikes of the brain from the scalp of the human users. And then the next step is where the AI comes into the picture. So that's where we actually try to make sense of all these data, brain signals that we have collected, in order to identify the needs, the wishes, the intentions, the mental states of that user. And then once our AI model makes a prediction, that is sent to the external device. And one important element there is that this device gives either visual or auditory or haptic feedback to the patient or the user, right? This is what in research we call the BCI loop, or the neurofeedback loop. Now, a bit more about the neuroimaging part. You might ask, well, what does this brain signal you're talking about look like? Well, it generally looks like this. Lots of spikes that go around. Honestly, just by looking at it, you cannot make sense of it much. What we, as neuroscientists, do, we actually have to look for meaningful spikes within all these patterns that we see there. So every row you see here, so here you have multiple rows of waves. Each of them come from one of these tiny electrodes that are placed on your implanted chip or on your wearable technology. And then we'll look for specific signals, specific spikes that we know are related to specific visual stimuli or intention that the user has had in mind. And then on the AI side, what we have most often is machine learning. How many of you have heard of this term, machine learning? Of course, yes, it's the hype terminology now related to AI. Everybody knows about it. What we do here with machine learning, although it's called machine learning, for us it's mostly the human telling machine what to learn. So as you can see here, there is a human, normally computational neuroscientist involved, who already knows about the association between those neural spikes and what they represent in the brain. And then they tell the AI model, learn this pattern from the data, and next time you see it, then you know that your patient or user is thinking about a movement, or they are stressed, or they are going through a tough period of fatigue, or under vigilance. We are lucky that these days we live in the world of deep learning as well. So deep learning has been a gift for neurotechnology, improving the performance of these systems. And the reason for that is that the involvement of the human researcher in the training of the AI model has become minimal. What deep learning does, actually, it was part of the discussion in one of the earlier talks. It's a black box where we give all these data to, and we tell it, OK, learn it on your own. So it makes all those associations that we used to do as the researcher on its own. To better understand it, I have brought you an example. So let's imagine you want to teach the AI model to differentiate between images of kittens and puppies. One way to do it is that you tell the AI model, look for pointy ears and pointy eyes. If you see it, that's a kitten. If you see flappy ears and rounded eyes, that's a puppy. Yes, of course. Many images the AI model can do well. There might be a dog image without flappy ears. The AI would fail. But then with a deep learning technique, what you could do is to give it thousands of images of kittens and puppies and say, OK, learn the features on your own. Then this black box could pick up on the ears, on the eyes. It could also notice that triangle nose of the kittens versus the rounded nose of the puppies. So the model learns all those features on its own. And it's really a true gift for us, the neural engineers, because then we don't need to go through all that pain of understanding different patterns that come from many, many different mental states of the humans. OK. So far, so good. I hope you now all understand how the technology works. Now I want to ask, where is it applied? So of course, we started with the example of the patient. That's where actually neurotechnology emerged from. The main need for neurotechnology and brain-computer interfacing was the medical domain. You see here before you a tetraplegic patient, a person who had lost mobility from neck down, now being able to walk again and move their hands using this brain-controlled exoskeleton. That's a huge feat, right? It changes the quality of life for these patients. It gives them new mobility and interaction possibilities with their family members. So that's basically the utmost application domain for the technology. Another application domain that also falls under assistive technology is in a stroke neurorehabilitation. So again, this is another form of paralysis that comes after stroke. Sometimes people also remain with clenched hands. And we know that for long, physiotherapy was the only option for these people. These days, neurofeedback technology is providing them an option to stimulate the neuroplasticity of the brain. How it works is that the patient must think and imagine movement. The system, the AI model, would translate that imagination of movement, and then they would receive electrical stimulation similar to what passive physiotherapy would look like on their clenched hand. And that's how they will restore some of the lost motor functions. So yes, assistive technologies, that's where most of the application lies in. But what is it in it for us, the healthy people? Well, the good news is that there are many application domains for the healthy people as well. Neurotech can be used in digital learning technologies. It can be used in gaming, recreational activities, and entertainment. It can be used in neuromarketing. I understand that many of you are from business domain, and the good news for you is that neurotech can enable you to understand consumer psychology better. It can be used in sports analytics, and finally in research. And by research, I mean psychology domain, cognitive science domain, and anything that falls under theoretical science. So I would like to give you some examples. With respect to learning technology, one of the first examples is in critical operational fields, when your user, your learner, needs to learn very complex tasks. An example of that is in pilot training. Have you ever been in a cockpit of an aircraft? good. You know, it looks enormous, and it's very overwhelming with all these buttons and screens that the pilots have to operate. So pilots must master multiple procedural tasks. They have to be prepared for disaster management, right? And it takes a huge workload for them to be prepared for such scenarios. So one of the works that we do right now in our lab is a collaboration with the Royal Netherlands Air Force, where we are creating these brain-computer interfaces that monitors the workload of the pilots when they are going through different training scenarios. And the idea is to develop personalized training cases for them so that they don't fall into that overload state of mind. And that's very risky. If you fall in that overloaded state of mind, you do not learn anymore. In fact, there is a known phenomenon with the pilots where they no longer hear any alarms in the cockpit because of all the sensory information they have to process at a time. And that could lead to fatal accidents, right? So in this project, what we are focused on, we would like to use neurotechnology in order to enhance the training and the performance of the pilots. The next example is in classic classroom or lecture scenarios. So how many of you remember what I just said in the previous slides? Maybe some of you already might wondered, right? Maybe some of you are already drifting away. What are they going to give us for lunch, maybe? What is my family doing right now? Yeah, it's hard for the human brain to sustain attention for a very long time. And if you would like to learn something, the sustained attention is the most important mental state you have to be in. In one of our projects, we actually want to give this ability to virtual tutors, to tutor agents in form of embodied robots or virtual avatars, the ability to monitor the attention level of the students when they are learning a new task. In this case, we taught them a fake language. And then what we saw is that when they were wearing the neurotechnology and the behavior of the robot, the content of the learning task was adapted based on their attention level, they actually remembered the information from that task more than the people who just randomly received those gestures from the robot. So in fact, personalized training, personalized learning tasks using the neurotech can enhance the performance and cognitive abilities of the learners in this scenario. Okay. The next scenario, which I think many of you might like if you are a professional gamer, is the use of neurotech in gaming industry. So one way to recreationally use neurotechnology, particularly non-invasive EEG, is to control these digital games with inputs from your brain. And this does not mean that you no longer need your hands. Of course, you can continue using the joystick, but there are some scenarios where you think that, you know, the game could just pick up what you might need extra from the attention you pay to a certain stimuli in the screen or in the game environment, and that could bring in additional input to your game experience. Another way we use neurotech in games is where we look at multiple gamers, multiple players in a certain game, and we'll look at the synchrony, the neurophysiological synchrony they build up together in order to have better performance in that game, which is really good because it can also be used exchangeably when you need to train people for certain training scenarios. And then one of the examples we actually did with my team in the lab was to create a game for attention training. So we know that these days we have a lot of kids with ADHD. These people suffer from attention deficit hyperactivity disorder. And the problem with them is that it's really hard to focus, to sustain their attention. Sustaining attention is difficult in general, but with this new world where you have all this stimuli information lying around you, it's even further and harder. So this game, what we did is that we provided some of the visual stimuli that were presented in the digital environment, and the task of the user was to focus on them in order to get a reward. And neurofeedback had already been established as a good way, as an effective way to help ADHD people with ADHD, to train for better attention. What we found in this study was that gamified neurofeedback, where you have the input of your brain connected to the game, could even further enhance the effectiveness of that intervention. And then one more recreational activity, neurotech in drone control, right? Well, this image that you see here actually comes from a study that did it just for the purpose of entertainment, but I know of my colleagues who actually work together with defense sectors and military in order to measure situational awareness in drone pilots. And that's another way that you can actually enhance people's cognitive abilities when they must perform well. And then one of the other examples I talked about was neurotech in a sports training. If you are an athlete, a professional athlete, you know that sports training is not limited to physical training. You also have to maintain mental imagery of all the techniques and the moves you must learn and perform. So during the time that athletes are not doing the physical training, what they do, what they are told is to actually rehearse everything they were doing in the court. And in fact, for such athletes, we could offer this sort of neurotech-based training scenario where they can just sit at home, have a gamified environment, start rehearsing all those techniques they learned in the actual field, and then see the visual outcome of that in the game. This is what we call mental imagery training, and that's only possible if you have a way to connect the brain to the external world. And then finally, neuromarketing, before I get into research, is the science of understanding consumer preference using their brain and neural signals, right? Some of the neuromarketing companies, especially the one that I collaborate with in the Netherlands, right now are working on understanding people's preference toward packaging that different retailers offer based on the attentive mind state they have when they watch these different products with different packagings. So if you show a specific spike that is associated with high attentiveness toward a certain packaging, this means that your brain is going to pick up more information from that product. And that's what normally the retailers want, and they come to this company to have some consultants and have them test some of their designs. But what we do with them is actually different. We are more interested in understanding how information related to sustainability of the product is going to change the attitude and approach behavior of the consumers when they watch and interact with the product. So I actually think that this application of neurotechnology in neuromarketing is not just for the benefit of the seller. We can actually use the technology for good to develop these pro-environmental behavior change interventions, whereby tuning the information of the product, we can actually encourage and motivate people to act more sustainably. And this is where that actually my passion comes into the picture, neurotechnology and research, particularly psychology research. This is a study we did on creative thinking, where we were interested whether doing problem-solving tasks in virtual environments would activate those areas in your brain that are associated with creativity more than when you're doing this on a computer screen. Right? This is a very important skill. Creative thinking is the skill that you will require for this century in order to survive. And if we can have these digital environments that help you with creative problem solving, then I think that's something people would want to have. And what we found was actually, it's true that 3D information, 3D media can activate those brain areas more than the 2D information that you receive on a screen. And one more important topic in the research domain is embodiment and body ownership. So imagine for some time, a patient, an amputee, did not have a hand, and suddenly they are given the opportunity to operate and control a neuroprosthetics. Do you think that they're going to accept this new hand as part of their body schema very soon? Well, that was a question that we researchers in the BCI domain had for some time. Actually, this was a topic I worked on during my PhD research. And the answer is yes and no. You don't really incorporate this new body, this new limb into your body scheme early, but with enough training, after a while, some of the representations in your brain are susceptible to change. And then that's when you start feeling that this new part that doesn't look really human-like has become part of you. And I have an example here for you how this can be like groundbreaking for some of the patients. Here you have a paralyzed patient that has received an implanted chip and has been trained for months and months to be able to control this robot arm to go to left, right, up and down. And this is what happens.
In a day, literally a day. The highlight was 45 minutes ago. I got to use a robotic arm for the first time, and I got to reach out and touch somebody for the first time in 7 years. You know, reaching out and touching my girlfriend for the first time and holding her hand. That was my highlight.
Okay, yeah. You see, sense of embodiment matters. So it's not just about reconnecting with the world and manipulating stuff and objects. It's also about communication and being able to touch loved ones again. All right, so I am going to skip to the challenges. So there are 3 challenges that I currently see in the domain, which requires further development and research. The first one is this neurotechnology system performance. The reason that we don't see everybody walking around with an implanted chip or wearable EEG opening the doors just with their brain command is that these systems do not really operate 100% yet. And we talked about the AI models and how much data they need to be trained. And we yet do not have that data. Our hardware is also not yet fully developed in a way that it can cancel out the noise that you have from the environment. So there is a long way to go in terms of development and research for us to finally have the mainstream adoption of these systems. The second thing that hinders the application of these systems is the individual differences. We all have different neuroanatomy, different lifetime experiences, and hence different brain signals. It's really hard to train an AI model to understand the same mental states that I have as the same mental states you have and everybody else. So we need a lot of data from the same person, and our data from that person could also be different from day to day. So that's another challenge we still have with these systems. And finally, the ethics and regulation. I want to elaborate on this slightly more. There is no lecture that I give about neurotechnology where I'm not asked about brain hacking. Everybody would have this question, what about my neuroethics, my privacy of the data? And that's a valid concern, that's a valid question. But I actually want to introduce to you some of the other ethical questions that you might not even think about, and I'm going to leave you with those questions. In fact, the ethical questions regarding neurotechnology fall under 3 categories: physical considerations, psychological considerations, and societal considerations. In terms of physical consideration, Is it even safe for us to proceed with these neural technologies and neural implants? How is it going to impact our brain, the anatomy of our brain, the autonomy of the person, and generally the acceptance of these metallic devices into the brain tissue? The second one, as I already touched upon, is the personhood and the agency of the person. Would the agency of the person over their body change over time if they are equipped with new devices that are not part of their body, becoming like a cyborg, as we see it in the movies? What about the privacy and neuro rights? We already talked about that. The moral and legal implications. One example that I really like in this case is that what if your neural prosthetic slaps another person? Yeah, things happen. AI models make a mistake, right? Who is responsible for that? The neurotech company or the user? And then the other problem is a stigma and normality. If it becomes normal for everyone to have a neural implant and then you do not want to have it, then what happens then? If you are a patient and you refuse it, are you becoming a burden to the economy and society? How are you dealing with those feelings? And finally, how can we maintain justice and fair access, right? So what if all of us have access to this and now we are experiencing an era of enhanced cognitive abilities among humans, whereas in other parts of the world, we are seeing another generation of humans with the basic abilities that we used to have. What about that? So these are the questions that I'm going to leave you with. Thank you for your attention, and I'm happy to take your questions.
Thank you very much, Maryam. That's all we've got time for, I'm afraid, but thank you.
Yeah, thank you.